guys, so welcome back to another video, and today we're going to be looking through a few things. So first of all, we're going to be looking at power series. We're going to look at power series but with a centered term, kind of it centers around something. I'll explain how that works. And then we're also going to be looking at the interval convergence and the radius of convergence, like radius of convergence, interval of convergence, and we're going to be looking at a convergence theorem for the power series that is centered. And I believe I'm going to do a few examples of that, finding those, and then we're going to touch really quickly on how you can represent any series as a function, and that's useful because then you can do limits and differentiation on that, but we'll get onto that later. Okay, so let's start off for the definition of a power series. So a power series has a form like this, where you kind of have Cn, there's some kind of coefficient, right? It's going to be it could be like, for example, 2 to the n, for example. That could be 2 to the n. Cn could be 2 to the n, and it's going to have different coefficients. And then x to the n would be some other kind of they're technically two coefficients, but we're splitting them in half. You'll see why x is there, because technically I want to point out really quick that what's changing here is n, right? X is not changing. X could be any number. Like we could say x is equal to 2, and it would be Cn multiplied by 2 to the n. So x is just any number that's going to be constant throughout the whole power series. The only thing that's going to change is for some values of x, like just really quickly, like for example, x could be, for example, from -1 to 1, and any values there, this would converge. But then x outside of 1, so therefore x equals 2 or -2, then the series would diverge. That's why there's an x there, but the x stays constant throughout the whole, like every single x here is equal to each other. It's x to the power of 0, x to the power of 1, x to the power of 2. So anyways, let's keep on going, and I think these are not very important to know, except the fact that exactly what I just said, that this thing converges for an x in some interval. So x from -1 to 1, for example, that is an interval, and this series, a power series, would converge depending on the interval of the x. That is what we call the interval of convergence. But we're going to get there later. So now we're going to look at a new form of a power series here where there's Cn x minus alpha, or a, to the power of n. And basically it's centered. So what we would say is this is a power series that is centered at x equals alpha, or x equals a. And the way it works is, if, for example, you had a sum, right? If you had a range of x, let's say x could vary, x minus alpha could vary from -1 to 1, right? Let's say that's the interval of convergence. Then what's going to happen is, if you do all the sums, let's say x is equal, or x minus alpha is equal to -1, right? You're going to have a sum here, and then if you, like, everything else out here is divergent. But if you had this here, it would sum at some, let's just say it sums at -1. And then if you had x minus alpha is equal to +1, then the sum would be 1, right? And then whatever it is, it ends up being centered at alpha. And this is just to say, I believe it's x minus x equals alpha is at the middle here. Like whatever the sum you get from saying x equals alpha, which honestly just means x minus, if x is equal to alpha, for example, you'll have 0, right? And the sum would be 0, so it's definitely convergent. So that's another idea about these power series but centered, is if you had a centering kind of term, if x is equal to that term, it all turns to 0, it converges. So it converges here will just be when x is equal to alpha. It's centered around that point. And then all the different sums from when x minus alpha is equal to -1 to x minus alpha is equal to 1, those are on both sides, but it's centered around when x is equal to alpha. So that's the idea. That's why we say it's a power series that's centered around x equals alpha. Okay, so let's do a few examples of this, and you're going to see exactly kind of how it works. I wrote down a few notes here, but generally kind of it's exactly what I'm saying, is like, it's just different values of x, and you'll see this. So let's say we find the center of this form here, where it's 2x plus 1 to the power of n, right? what we want to do, this says center, so obviously this would be a power series that has a center, and then find the interval where the power series converges. So in other words, finding the interval of convergence. So let's look back at the form that we're trying to work with. We're trying to get Cn multiplied by x minus alpha to the n. So we want to manipulate this to be in the same form of Cn to the power of, multiplied by x minus alpha to the power of n, right? So how are we going to do that? Let's look at this. So we have 2x plus 1 to the n. Let's take 2 out of this equation. That leaves 2 to the n, multiplied by x plus 1/2 to the power of n. And if you want Cn is going to be 2 to the n, and then if you want x minus alpha, then you have to do minus. So here you would say it's 2 to the n multiplied by x minus 1 over 2. So 2 minuses because the form is x minus alpha. And so therefore, this series would be centered around alpha equals minus 1/2, right? Okay. So now we want to find the interval where the power series converges. So what we got to do, I believe, is do... Okay, yeah. So we know for sure that this is kind of like... let me show you guys really quick. This itself is a geometric sequence. Okay, so for example, if you had, again, it looks a bit different because x, you would expect x to be a variable, but it's not. It's actually a constant. So you could say x is equal to 10, for example. Like there's values of x where it does converge, but let's just pretend x is equal to 10, right? This would technically turn into just 20 plus 1, which is just 21 to the n. And so the series would be 21 to the 0, which would be 1 plus 21 squared plus 21 cubed, right? That's a geometric sequence. So by looking at the form of this equation here, 2x plus 1 is the common ratio of the geometric sequence. What you'll have is 2x plus 1 all to the power of 0 at the start. That's going to turn into 1. 1, then plus 2x plus 1 to the power of 1, then plus 2x plus 1 to the power of 2, right? And that's going to keep on going. And whatever it is, this here is the common ratio. This is r. And if you remember anything about geometric sequences, it's that the common ratio has to be less than 1 for it to be convergent, for the absolute value of that for it to be convergent. So what we're going to do is we're going to say that the common ratio, 2x plus 1, that the absolute value of that has to be less than 1, meaning that it's going to be more than minus 1 and less than 1, right? And you can split this into 2, say that 2x plus 1 is larger than minus 1, which is one expression, and then the next expression is 2x plus 1 is smaller than 1. You solve it. What you end up with, let me just make this really quick. So let's say you minus 1 from everything, right? Minus 1 is minus 2. 2x plus 1 minus 1 is 2x. On the right side, you have 2x plus 1 minus 1 is 2x, and 1 minus 1 is 0. And then you do all that kind of stuff. You end up with x existing between minus 1 and 0. And so any value of x, as long as it is between minus 1 and 0, right? You can put back here, you could put minus 1, you could put 0, you could put minus 0.5, you could put minus 0.25. As long as it's between that range, you put it into x, this whole series is convergent. And that's the kind of idea that we're working with when we're working with like a power series with an x term inside it. So yeah, I think, okay, so now we have the power series converging theorem. So we just have a power series that is centered at alpha, which is just the form that we have before, right? Cn multiplied by x minus a to the n, x minus a to the n, right? And there is exactly 3 things that can happen, and one of those 3 things has to be true, right? Exactly one of the following is true. 1, this series converges only for when x is equal to alpha. The only time when it converges is when x is equal to alpha. And that kind of makes sense, right? If x was equal to alpha, then it's alpha minus alpha, that's all to 0. And then you have Cn multiplied by 0 forever. So the infinite sum would just be 0. And so the first situation is that it only converges for when x is equal to alpha. The second scenario is that there is a number r. We call this the radius of convergence. And it's a little bit similar to the interval of convergence. There's slight differences, but I'm going to explain it really well, let's read this first. There's a number r, radius of convergence, that is larger than 0, so that the series right here converges for when the absolute value of this term here is less than r, right? And diverges for when this term here is more than r. It's the same thing where we said like the common ratio has to be less than 1, for example. This is just for this. And each series is going to have their own special little r. And so yeah, you can have x minus alpha is less than r. That's convergent, right? That's the same thing as r being less than 1. And then it will diverge for when x minus alpha is larger than r. Okay, let's see. And then, okay, so that's the second scenario. And then there's a third scenario where it just converges for all x's, right? There is no limit. And here r would be equal to infinity, right? X minus alpha is less than infinity if it converges. And that's going to be all terms. So those are the three scenarios. So notice that there is no scenario where the series is divergent, which makes sense because even if there is no x value that can exist, at least there is one, which is one, it's going to be equal to 0. So this series technically can never diverge. Now, the trick is when you work with this, there's different nuances that you're going to have to find. They're not going to ask you, is this series divergent or not? Because the answer is 100% yes, because it's centered around this. Therefore, when it is equal to alpha, it is convergent, no matter what. But remember these three scenarios, and I'm going to explain really quick what radius of convergence is and interval of convergence, and then we're going to look at the nuances with this series. So the r means the radius of convergence, ROC, you see it down here, and the I is the interval of convergence. So basically, everything is centered around when x is equal to alpha, and then there's a radius of when this is convergent, and then outside of the radius, it's going to be divergent. So yeah, when x is equal, or when x is less than r, when x minus alpha is, for example, when x minus alpha is less than r, then it's going to be convergent. When it's more than r, it's divergent, which is when it's out here. And this is just to illustrate kind of the interval of convergence, the radius of convergence. They're basically almost similar, but it's just there's a slight difference between the interval of convergence and the radius of convergence. We're going to see that in a bit. So I want to note that there's no info for if x minus alpha is equal to r. So if we look over here, right, it only says less than or larger than. What about when x minus alpha is equal to r? There is actually no info, and you have to do another test. You just have to do a test to tell if it is convergent or not at those ends. And what are the implications of that? Right, the implication is that you have this range, you have this radius, right? The radius says you can go from alpha, you can go from the center out to r and to the r on the right, right? Alpha minus r, alpha plus r. But it doesn't tell you what's going to happen at these points. That's why they're hollow. That's why I drew them as hollow. You know that out here is divergent for sure. You know that in here is convergent for sure, but you have no idea what's going to happen at the ends, right? So, let's say that you had x minus alpha is, and then you had r is, let's say you had r is equal to 1, for example. You actually don't know if the convergence is when x minus alpha is less than or equal to minus 1, right? It could be like this, less than or equal to minus 1, and larger than or equal to minus 1, and then smaller than or equal to 1. You don't know if it could also be x minus alpha is larger than 1 and less than 1. You don't know that because the radius doesn't tell you what happens at the ends. So you can end up with a funky situation where you have x minus alpha is larger than equal to minus 1, but then smaller than 1, right? So you can see all the different nuances that can happen because r doesn't tell you what happens at r. And so, again, these are the possibilities. Just a quick recap, the square brackets means it's inclusive. The rounded brackets means it's non-inclusive. So, for example, if the range was x minus alpha, and then the range was from minus 1, it's larger than minus 1, but then it's smaller than or equal to 1, then that would mean that it's not inclusive of minus 1, but inclusive of 1. And that's the range. The square bracket is inclusive. So that's just another way of saying, but there's 4 possibilities. Again, when they're all inclusive, when they're all non-inclusive, if one of them is inclusive on the left side and one of them is inclusive on the right side. So though we have to test the ends, like test when x equals r, for example, because what happens is when x is equal to r, that's the ends of it, right? The ends of this, we don't know what happens at the end. So we have to sub in x equals r and then test the series to see if it's divergent or convergent. So let's do a quick example. I think we only have 2 examples, and then that should be good, or 3. But we'll look through them really quick. So we want to find the interval of convergence and the radius of convergence for the series x to the n over n. So really quickly, what we want to find is let's find the interval of convergence first, I believe. Yes. So let's use the ratio test, right? And because the reason why, again, we spot that it's a ratio test is that x over n, if you do the ratio test, it's going to be x to the n plus 1 over n plus 1 over x to the n over n, right? And that's really easy to cancel out. So that's why we use the ratio test. If you don't remember, the ratio test only works with the absolute convergence, so we have to do absolute values. And if you have, you're basically looking for the difference between the next term and the now term. It's like finding the common ratio. This is an analog to the common ratio of a geometric sequence. You're finding the multiplier between the nth term and the nth plus 1 term. We do all this math. Again, this is quite simple. You take the absolute value of x out, and then this, if you do L'Hopital's, the limit to infinity turns out to be 1. And so what you have is the ratio between them is L is equal to the absolute value of x. And since the absolute value of L, just like the absolute value of R, has to be less than 1, that's the basis of the ratio test, then absolute value of x also has to be less than 1. And therefore, you know that the radius convergence, right, x, it's going to go out by 1 and 1, right? It's going to go back to -1 and 1. But you don't know if it's going to be inclusive, or you don't know if it's like non-inclusive or inclusive of those points. And therefore, we only know that the radius of convergence is 1. But we do not know what the interval of convergence is. To remind you, the interval of convergence could be -1 and -1 and 1, but like 1 is inclusive, -1 is not. So we gotta test for those. So let's look at the interval of convergence and let's test for each of those situations. So first of all, we test for when x is equal to -1. That's this extreme end. So we do -1 in here. That's an alternating series. So let's first try the alternating series test. So this is basically saying, is the next term smaller than the previous term? Is it a decreasing series? And what we find is that the next term, n plus 1, is smaller than 1 over n, right? That's true. It's a decreasing series. Next, is the limit to infinity 0? Yes, it is. -1 to the n is just -1 or 1. One of the either absolute value is still 1. The denominator turns into infinity, and so that's equal to 0. So definitely converges at -1. We know that it's convergent at -1. What about for when x is equal to 1? That's this side right here. Well, when x is equal to 1, that's simply the sum of 1 over n to the n, 1 to the n over n, right? And that's the same thing as 1 over n. And if we do the integral test from 1 to infinity of 1 over n, we know it's divergent. It's this one where n to the p and p is less than or equal to 1, that's divergent. So since this one technically is n to the 1, that's divergent. We know it's not inclusive of 1. Therefore, we know that the interval of convergence is inclusive of -1, but not inclusive of 1. And then you can write it out like this. So now that I think before, all this information leading up, it's a little bit confusing as to the difference of the radius of convergence and interval of convergence. Hopefully, after seeing this example, you kind of understand what the difference between them is, and that's kind of what the question is going to be asking you, is finding the radius convergence. You do some kind of test to find the range of those things, and then you do the interval convergence test. So you test for the ends to find what the actual interval is. Okay, so we're going to look at another example here. This is a power series, I believe, but centered. No, this is not necessarily. This is technically, it centers around, I think, centers around 1. It centers around 1. So you end up with that kind of like x minus alpha kind of form. So let's look at this. We have this, right? We want to find the radius of convergence and the interval of convergence. Again, you see that the top term, whatever it is, it could be like a bajillion things, but it's to the power of n, and the bottom is n to the power of something, right? This, again, when you have this to the power of n plus 1, over n plus 1 to the squared, like it's going to be very easy to cancel these things out. So we're going to again use the ratio test, same idea as before. You guys can pause to look at the math, but the idea here is showing you guys what the philosophy behind what we're doing is. So we end up with this. We have this. Remember that x is just a number. It's just a constant, and so therefore it's not subjected to the limit, right? The limit doesn't matter. You can take it out. It's just a constant. You end up with this. If you do L'Hopital's and that kind of stuff, that turns into 1. You don't do L'Hopital's with this. You expand the brackets, you multiply it by 1 over n squared over 1 over n squared. You can try doing that yourself, but trust me that it comes out to 1. So you know L is equal to the absolute value of x minus 1, therefore x minus 1 must be less than 1. So you know the radius of convergence is, again, 1. So yes, yeah. And this is just saying that you should keep it with the definition from above. So this is x minus 1, remember it's x minus alpha less than r, right? And you don't have to like plus 1 to both sides. You make this x0. It doesn't matter. What we're looking at is the radius of convergence to the definition of that, and it's x minus 1. Obviously, the previous example, it wasn't centered around anything. If you notice, this wasn't like x minus 1 all to the n. It's just x. In that case, we don't have to. But in this case, let's keep the minus 1 here. And let's test for when the extremes of this. So when x minus 1 is equal to minus 1, and when x minus 1 is equal to 1. So you get x equals 0, x equals 2. When you get x equals when x equals 0, what you end up with, if you remember what it is x minus 1 to the n over n squared. And when x equals 0, it's just minus 1 to the n. Again, alternating series. Let's use the AST. You find that it's convergent, yes. And then here, when x is equal to 2, you have 2 minus 1. Again, it's 1, but 1 over n squared this time. Again, remember the integral test, the p-series kind of thing. This is convergent. So it's inclusive of both sides. Then we do square brackets for both. That's the kind of idea. I think this, again, this is the same thing. You do all those kind of things. I guess this is pretty interesting. So let's find L. This is actually pretty interesting. So this is x to the n over n factorial. We've done factorial. If you've seen the last video, you would have seen all the ways to do like this kind of stuff, the ratio test and stuff. But what we end up with is that we find that L is equal to 0. So what does it mean that L is equal to 0? Well, there's a note here. I don't know why this is true, but let me think. Oh yes. This is what L means, right? L means that L is equal to the difference between the first coefficient and the second coefficient. Yeah, if you remember, it's c to the 0 plus, if we had like if we had this, it would be, oops, okay, that's my bad. If we had this, right, it would be, the series would look like c to the 0 plus c to the 1 multiplied by x minus alpha plus c to the 2 multiplied by x minus alpha squared, that kind of stuff. And x minus alpha is just a constant, right? It's like 2, 4, right? So it's just a constant to the c. So basically, the L, when we're doing something like this, when we're doing the ratio test, we're basically finding the limit between each of those coefficients. And therefore, the radius of convergence is 1 over L. I am not sure why it is, but that is true. That is true, something we've learned in class. But I'm going to think really quick, for 5 seconds if I can find it. And if I can't, we're just going to take it as truth. Okay. I suppose that basically it's kind of like, what I'm thinking is, if L, right, the idea is that, is it a decreasing series? I think that's the main idea, is what we're working with a decreasing series. If L, for example, let's say L was equal to 2, right? That means that for every next term, you're multiplying by 2. The radius would mean that it's 1 over 2, which is a half, right? Meanwhile, if L was really small, like L was like 0.5, for example, which is 1/2, well then R would be equal to 1 over 1/2, which would be equal to 2. So smaller the ratio between the two, the smaller the differences between the things, the less it diverges. And so there's a larger window for that being convergent. Does that make sense? So if the ratio between the two, which is what L is, that's what we're finding with the ratio test. If the ratio is really large, it means that the number is jumping a lot. If it's jumping a lot, there's a really small window for it to be convergent. Meanwhile, if L is really small, then the window for it to be convergent is really large. And so the radius is going to be really large. That's why it's a reciprocal relationship. So basically, that's the kind of idea. Still, I can't prove this for sure, but this is what our teacher told us. But basically, R is going to be equal to 1 over L. And we found that this one, L is going to be equal to 0. So 1 over 0 is infinity. And if R is equal to infinity, then that means that the series converges for any values of x, right? So yeah, that's exactly what happens. So this thing converges for every value of x. I don't know if we should get into this because this is like another kind of idea. I'm gonna go through really quick just to say this, but I don't think I'll include this in the video title, and you can probably leave this video because I'm gonna make a new one once we learn about this in class. But there's a theorem that says that you can represent any of this kind of power series as a function, right? Function that exists on some interval I. So if for example like x is less than or equal to 1, right? So and you had a function, if you found that this is the interval of convergence, then that function, whatever it is, only exists on that interval as well. Like it would only exist when x is equal to -1, between that to 1. So that's the idea. If it was non-inclusive at the ends, it would be a circle and a dot here. So yeah, that's the idea. That's what I mean by on some interval I. Just erase this really quick. But yeah, you can represent it as any function. And if fx is both continuous and differentiable on I, which is dependent on whatever this form of function is, then you could differentiate it or you could integrate it, right? The whole idea of why we represent things as functions is if it's continuous and differentiable, we can integrate it, and we can if it's continuous, we can integrate it. If it's differentiable, we can differentiate it. So yeah, this is just an idea where this is the general form of a power series, and when you differentiate something, they're all just plusing each other, right? So by the nature of differentiation, this differentiates here, these terms differentiate here, these terms differentiate here. So you can see how, like for example, the power rule, 2 goes into the front. This is 2 minus 1, so equal to 1. That's the kind of idea. You can differentiate it. You can also integrate it. C0 turns into C0x. C1x minus alpha to the power of 1 turns into C1 over 2x minus alpha to the 2. So that's the idea. If you differentiate and integrate, you have a different p series. That's true. So the idea is that if you do this, and we're going to be doing this to kind of manipulate them and work with them easier, but basically what happens is that you will have a same radius of convergence, right? But by nature of it, you have a different series compared to before, right? It was C0 here, now it's 0 plus C1, right? It's a different series. And so you're going to have a different interval of convergence. So even though the radius of convergence will be the same, meaning that like if you remember the diagram, right, it's going to go out equal lengths to r, but then we don't know if it's convergent or divergent at the end. So if we found that the original sequence is convergent for both ends, we don't know if the differentiated version is going to be convergent for those ends as well. That's just the idea. And I'm just looking at a few of these. Again, this is more just kind of representations, but I'm just going to tease that really quick. I think none of these are really important. But yeah, I'll say thank you guys for watching this video. I know it's pretty long, but it's a really kind of it's a idea that takes a lot of explanation, and I think yeah, it warrants being this long. So thank you guys so much for watching. Hope you guys have a good rest of your day.